Good day. Welcome, my dear students, to the 8th lecture of Mechanics of Solids. And in this lecture, we will study about transformation of stress and strain. So, about transformation of stress and strain, we already studied about Cauchy's formula. Using Cauchy's formula, we can find the normal stress and shear stress values on an arbitrary plane. And if you know these 8 stress tensor components, 9 stress tensor components, using these 9 stress tensor components, we can calculate the normal stress or shear stress or any component of stress on an arbitrary plane using Cauchy's formula. Okay, similarly, we can use 9 strain components in the strain tensor matrix. That is also can be used to calculate the strain on an arbitrary plane. And the importance of the stress transformation, stress and strain transformation, is that in some case the reference planes, here our reference plane is x plane and y plane and z plane, and those reference planes need to be changed to some other orientation. Okay, maybe in some situations we need to change this reference plane x, y and z planes into some other orientation. So changing this reference plane to a different orientation, okay, leads to the change of components, stress components. These 9 stress components change with respect to the changing the reference planes acting along the reference axis. Okay, so here we are not changing the point, so the point is fixed, and this is the axis, 3 axes passing through this point x, y, z, and we have 3 planes, x plane, y plane and z plane. Okay, we have 3 planes, and these 3 planes is the reference plane for these 9 stress components. So in some situations we need to change these planes, reference planes or reference axis. In that case, these stress components also will change with respect to the changing of this reference plane and axis. These 9 stress components also will change. So next in this topic, we are going to calculate, or we are going to find this change in stress component with respect to the change in reference planes. Okay, so for example, this is my point. In that point, this is the x-axis, y, and this is my z-axis. Okay, x, y and z axis, and here I am changing the reference axis. So this is my reference axis x dash, and this is my reference axis y dash, and this is my reference axis z dash. Okay, and while changing this reference axis, reoriented this reference axis with respect to this axis, the plane also, the reference plane also will change its position. Okay, so for x, y, z planes, x, y, x, z, y, z plane, we have these stress components, 9 stress components in the stress tensor matrix. But if we change this reference plane or reference axis, with respect to that, the stress components also will change. Okay, and we are going to calculate what is the change in these stress components, which is acting on along in this axis. Maybe this normal stress is acting in this direction, sigma x dash acting in this direction, sigma y dash is acting in this direction, the no stress component, and the sigma z dash is acting in this direction. And similarly, the tau xy is acting in this direction. This is another direction. So every stress components in the stress tensor matrix will change its position. Okay, for that we use transformation of stress and strain. So for that we are using plane stress condition. So you know what is plane stress condition. In the plane stress condition we only consider the stress acting on two planes, or the stress acting on a particular direction is considered as 0. That means, for example, the stress acting on z direction, that is sigma z, tau xz, tau yz is considered as 0 in case of plane state of stress. So here in this analysis we use plane state of stress. So here we can see a bar, and in this bar, that is in the xyz coordinate, xyz Cartesian coordinate, and inside this bar I consider a very small cube. This is a cube inside the bar, and this bar is subjected to some external stresses, that is sigma x along the x direction, sigma y along the y direction, and sigma z is equal to 0 because this is a plane stress condition. Okay, and some shear stress values also acting, tau xy acting on the four faces of this cubical element. So this is in the x, y, z plane, and here this cubical element I am going to orient this cubical element into a new axis system, So there is no change in this bar, but the cubical element position is changed. So this is the original axis x, y, z, and after rotation of the cubical element, the axis of this is shifted by an angle theta. So this is x dash and this is y dash. X dash making angle theta with the horizontal, and similarly y dash also acting make an angle theta with this vertical. So this is the new oriented position of the cube, and here we are going to calculate what is the normal stress on this face. Initially in this face the normal stress is sigma x, but after theta angle rotation, what is the normal stress on this face? That is the transformation, which transform the axis by an angle theta. Okay, by angle theta. So after transformation, what is the normal stress acting on this plane? So that is sigma x dash. Similarly here it is sigma y dash. The normal stress acting on this plane is sigma y dash. After transformation, what is the normal stress acting on this plane? It will change. So you can see this is the y-axis. So there is an angle difference between these two, y-axis and sigma y dash. The angle difference between these two is theta. Similarly, this is the x-axis. You can see this is the x-axis. The angle between sigma x dash and x dash is theta. Okay, similar to this axis system. So this is the transformation of stress and strain. So here I am not going to explain the derivation to calculate sigma x dash and sigma y dash, and even this tau xy also, because this is not included in your syllabus. So after some derivations we got this sigma x dash and sigma y dash. Okay, so that sigma x dash and sigma y dash is expressed in terms of sigma x, sigma y, tau xy and theta. Okay, after transformation of this plane, we got new sigma x dash and sigma y dash, and in the equation of sigma x dash and sigma y dash, the sigma x dash, sigma y dash, the new shear stress tau xy is expressed in terms of the normal stress, initial normal stress, the normal stress acting on the vertical plane, sigma x, sigma y, tau xy, and one more variable, that is theta. That is theta. So this sigma x dash depend upon sigma x, sigma y, tau xy, and theta, because theta is an important parameter, because when we change the position from this point to next point, for example, here the plane rotation or the angle made by this plane and the horizontal is theta. If we rotate further, then the angle may change from theta to theta 1. So when it changes from theta to theta 1, correspondingly the normal stress also will vary. So this sigma x dash, sigma y dash, and tau x dash y dash depend upon these three values, sigma x, sigma y, tau xy, and this theta value also. Okay, and this theta y also. So I am not explaining the derivation to calculate these three values. So this is a simple derivation. After resolving all the components along this inclined plane, we can calculate the stress on the inclined plane. So this is the final equation. So this is actually sigma x dash. Sigma x dash is equal to, so if this is sigma x, this is sigma y, and the shear stress acting on these two planes are tau xy, what is the stress on this plane? Just wait. What is the stress on this plane? This inclined plane. So this inclined plane make an angle theta with this vertical. Okay, so this angle will be theta. This angle will be theta. Okay, so then what is the value of this normal stress acting on this inclined plane, that is sigma x dash? And the same way the another face, this one, these two are 90 degree apart. This is sigma y dash. What is the value of sigma y dash? And the shear stress acting on these two plane, that is tau x dash y dash. What is the value of tau x dash y dash? So here, after the derivation, we got sigma x dash is equal to, that sigma x dash is a normal stress, that is why it is given sigma n1. Okay, sigma x dash is equal to, or sigma n1 equal to, sigma n1 equal to sigma x plus sigma y by 2, that is sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta tau xy into sin 2 theta. That is the value of this sigma x dash. Similarly, the tau x dash y dash. So next one is this tau x dash y dash, and to calculate this tau x dash y dash, this is the equation: sigma x minus sigma y by 2, sigma x minus sigma y by 2 into sin 2 theta minus tau xy into cos 2 theta. That is the equations to calculate this sigma x dash y dash, that is the shear stress on this oriented plane. The next one is then another normal stress sigma y dash. To calculate sigma y dash, this is the formula. This is the formula to calculate sigma y dash. Or this is the second normal. The first normal is sigma x dash. This is the second normal, that is why sigma n2. That is equal to sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 into cos theta minus tau xy into sin 2 theta. Okay, so by this theta angle orientation, from xy plane or xy axis, the new stress components are sigma x dash, sigma y dash and tau x dash y dash, and we can express this sigma x dash, sigma y dash and tau x dash y dash in terms of the stress components on three mutually perpendicular perpendicular planes, that is sigma x, sigma y and sigma y and tau xy. Okay, and one more thing, theta. So this is the three equations. So using these three equations, we can calculate the stress on any plane that is at an angle that is at an orientation theta degree with the original xy planes. Okay. So these are the three equations. So using this concept, we can calculate the stress on an inclined plane. Using this concept also, we can calculate stress on an inclined plane. So for example, this is sigma x, sigma y, tau xy is active. Tau xy is active. So for this system, for example, consider this inclined plane that is at an angle theta with this vertical. This inclined plane theta with this vertical. And what is the normal stress, or what is the stress here? The normal stress, that is sigma x dash, we can give this as sigma n dash or sigma n. What is the shear stress? That is tau xy, or we can give sigma t. That is a tau. Commonly we use tau, but we can use sigma t. That means tangential stress or shear stress. The t representing tangential stress or shear stress. Okay. So using this concept, we can calculate this normal stress and shear stress on an inclined plane. To calculate this normal stress, we can use our previous formula, that is this formula, sigma x dash formula. To calculate this shear stress on this inclined plane, we can use this formula. Okay. So using this two formula, we can calculate the normal stress and shear stress on an inclined plane that is at an angle theta with this vertical. Okay. This is the equation to calculate sigma n. Sigma n is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy into sine 2 theta. Similarly, sigma t equal to sigma x minus sigma y by 2 into sine 2 theta minus tau xy into cos 2 theta. So using these two equations, we can calculate the normal stress and shear stress on this inclined plane. And to calculate this normal stress, what are the input data required? We need the normal stress on this vertical plane, normal stress on this horizontal plane, the shear stress acting on this initially perpendicular planes, and this value of theta. That are the input values required. And similarly for sigma t also, the shear stress on this inclined plane. For that also, these are the input values. Okay. And similarly, we can draw another plane. For example, consider this plane. Consider this plane. This plane. And here also we can calculate the normal stress sigma n. Sigma n. Shear stress sigma t. Sigma n and sigma t1. And what is the difference between this plane and this plane? The only difference is the angle theta. Here, this is the angle, but here, this is the angle, theta 1. Theta 1 is the angle. So, by changing this theta value, the all other terms are same. Sigma x, sigma y, tau x, y, all other terms are same. But here, by changing or by orientation of this plane from this position to this position, or we consider next plane at an angle theta 1, the only change is this value. Here instead of theta, we should give theta 1 to calculate the normal stress and shear stress. So, similarly, we can draw infinite number of planes through this point. Infinite number of planes. And each plane has different theta value. Each plane has different theta value. And on each plane, we can calculate the sigma n and sigma t. Okay, the sigma n and sigma t value is different for each plane because when we draw another plane, the theta value will change. With respect to theta, sigma n will change. So for each plane, the sigma n and the sigma t values are different. Then my question is that we already discussed about principal stress. Principal stress is principal plane is the plane where this normal stress is maximum. Okay, principal plane is the plane where the normal stress is maximum, or we define principal plane with another term. What is that? We define that on a principal plane the shear stress value equal to 0. So there are two definitions for a principal plane. On a principal plane, shear stress value equal to 0, or we can say this is the plane where the normal stress is maximum or minimum. Okay, that is principal plane. And out of this infinite number of planes with the theta 1, theta 2, theta 3, there are infinite number of angles also there. There are infinite number of sigma n, sigma t values also there. Out of this infinite number of sigma n and sigma t values, or sigma n values, out of infinite number of sigma n value, there will be a plane where the sigma n value will be maximum. There will be a plane where the sigma n value will be maximum. And that plane is called principal plane. That plane is called principal plane. So how can we calculate this principal plane? How can we calculate the location of this principal plane? For that, we can use a concept that is, this is the general equations to calculate the normal stress on any plane that is at an angle theta. Okay, this sigma n is the general equations to calculate the normal stress on any plane that is at an angle theta with the vertical. Okay, so this equation also can be used to calculate the principal stress also. But we don't know the position of the principal plane. We don't know the angle between the vertical and to the principal plane. So next we are going to calculate this angle. Next we are going to calculate this angle. For that, we know on a principal plane the sigma n is maximum. Sigma n is maximum. For any maximum, for any quantity which is maximum or minimum, you already studied in your mathematics class. For any quantity which is maximum or minimum, the differential of that quantity with respect to the variable will be zero. Okay. For any quantity which is maximum or minimum, then at the maximum point or minimum point, the differential of that quantity with the variable will be zero. So here we can say at the principal plane, d sigma n by the here variable is theta, because we changing the value of theta for calculating the sigma n of different plane. So here the variable is theta. So on the maximum point or the minimum point, the d sigma n by d theta will be zero. Okay. So next we can differentiate this sigma n and equate it to zero. So this is the procedure. So here we differentiate sigma n with respect to theta and equate it to zero. So this is the sigma n. We differentiate that. After differentiation, we got from this equation, we got tan 2 theta p equal to 2 tau xy by sigma x minus sigma y. Okay. After differentiation, we got this equation. And in this equation, tan 2 theta p is equal to some numerator divided by some denominator. What is tan theta? Tan theta, Pythagoras theorem. Sorry, for a rectangle, tan 2 theta is equal to opposite side by adjacent side. So this will be, the numerator will be, if you consider a triangle with a 2 theta p as an angle, included angle, then this numerator will be the opposite side and the denominator will be the sigma x minus sigma y. So here I am constructing a triangle, a rectangle. In this rectangle, the opposite side, this is 2 theta p. The opposite side is 2 tau xy, that is numerator. Denominator is this sigma x minus sigma y. Here we can see the tan 2 theta p. What is the value of tan 2 theta p? Opposite side by hypotenuse. This equation is true. Okay. So the theta here, after differentiating and equated to 0, we change the theta value into theta p, because after differentiation the theta corresponding to principal plane, because on a principal plane sigma n is maximum, that is why we differentiate this sigma n with respect to theta and equated to 0. So after differentiation, this theta changes to theta p. So here cos 2 theta sin 2 theta by cos 2 theta will be tan 2 theta p, that representing the angle between, this is my principal plane and this is theta p, angle between the vertical and the principal plane, theta p. So we got this triangle. So I construct this triangle to calculate this cos 2 theta and sin 2 theta. Okay, to calculate this cos 2 theta and sin 2 theta. So here what we do, so we know the two sides of this rectangle. Using Pythagoras theorem, we can calculate this AB, hypotenuse, root of this 2 tau xy square plus sigma y x minus sigma y whole square. That is the hypotenuse AB. So this is the hypotenuse, root of this value. And then we can calculate cos 2 theta p. Cos 2 theta p. What is cos 2 theta p? That is equal to adjacent side by hypotenuse. Hypotenuse value is this one. Sin 2 theta p equal to opposite side by hypotenuse. Hypotenuse this value. This is. So we got these two values, cos 2 theta p and sin 2 theta p. Then we already find out the angle theta p. If we take the inverse, theta p is equal to 2 theta p equal to tan inverse of this value. That is the theta p. That is the position of the principal plane. Okay, that is the position of the principal plane. 2 theta p will be equal to, change the tan into opposite side, that is tan inverse of 2 tau xy by sigma x minus sigma y. That is 2 theta p. Again divide by half, we got theta p. That is the angle between this vertical and this principal plane, where sigma n is maximum. Sigma n is maximum. And next we are going to calculate the sigma n maximum. For that, just substitute this theta p in this equation, sigma n equation. Because this sigma n equation is the general equation for all planes. So we can apply this theta p value on this sigma n equation. But here, to simplify the calculation, instead of substituting theta p here in theta place, we substitute cos 2 theta and sin 2 theta. That is why I construct this triangle. So after this, I calculate cos 2 theta and sin 2 theta p. Then this two value can be supplied instead of this cos 2 theta and sin 2 theta. From that we can calculate sigma n, and if we substitute these two values here, this sigma n changes to sigma n maximum or principal stress. So that is this procedure. Here I am substituting sin 2 theta and cos 2 theta. And after simplification, so this is the simplification procedure. After simplification, we got this equation. That is the maximum normal stress or principal stress. Similarly, if we put a minus sign in between, we got minimum principal stress. This is a 2D case. So here we have two, in plane stress condition, we have only two principal stress, maximum and minimum. But in case of previous three-dimensional body, we have three principal stress. After solving the cubical formula, we got three roots: sigma 1, sigma 2, sigma 3. Those are the principal stress. But here it is a plane stress condition. We have only two stress, sigma 1 and sigma 2. So that is the maximum and minimum principal stress. So next, this is the two principal stress values, sigma 1 and sigma 2. Here we have only the stress components term, sigma x, sigma y and tau xy. So this is called principal stress. So this is the formula calculating. So if we know sigma x, sigma y, tau xy, then we can calculate the position of the principal plane sigma by knowing this angle theta p. So using this formula, we can calculate theta p. Okay, this is the formula to calculate or find the location of the principal planes, theta p. And using these two formula, we can calculate the principal stress sigma 1, that is the first principal stress, and by a 90-degree angle from this plane, by a 90-degree angle, this is the plane of minimum principal stress. This is the minimum principal stress sigma 2. Okay. from the plane of major, this is called major principal plane, that is at an angle theta p. Draw another plane that is at a 90-degree angle with the major principal plane, and this plane is called minor principal plane, where the next principal stress is acting, that is sigma 2. Okay, then one important point is that we already defined principal plane. On a principal plane, the shear stress value equal to 0. Shear stress value equal to 0. Next, we can prove is on this plane whether the shear stress is 0 or not. How? Just by supplying this theta p value on the shear stress equation. So we know the shear stress equation. This is the shear stress equation. This one is the shear stress equation. Substitute theta p on this theta, replace this theta 1 and with respect to theta p. So by changing this theta 1 with the theta p, we got the shear stress on a principal plane. But same procedure we can do. Instead of changing theta p, we change sine 2 theta p. Entire sine 2 theta p and cos 2 theta p. For that, again we use the data from the triangle. We already constructed triangle and we calculate the value of cos 2 theta p and sine 2 theta p. Substitute these two values. Substitute these two values on the theta p equation, on this equation. Okay, then we got the shear stress on a principal plane. What is the shear stress on a principal plane? And after substitution we got the shear stress on a principal plane. After the substitution we get which is equal to 0. So that is why we defined on a principal plane, the shear stress value equal to 0. On this major and minor principal planes, shear stress value is equal to 0. Okay. Then the next step is calculation of plane of maximum shear stress. Calculate the plane of maximum shear stress. So initially we know these three values, sigma x, sigma y, tau xy. So this is our principal plane, that is at an angle theta p with the vertical. Next we are going to calculate another plane. This is another plane that is at an angle theta s with the vertical. What is the main characteristics of this plane? In this plane, the shear stress will be, I am giving sigma t as shear stress, will be maximum. The shear stress will be maximum on this plane. In the previous principal plane, the normal stress was maximum. Or minimum. But in this plane, the shear stress is maximum. So next we are going to calculate this theta s. First we need to find the position of this plane. The plane which contains maximum shear stress. We can use the same procedure because we know the sigma t equation. Sigma t is equal to sigma x minus sigma y by 2 into sine 2 theta minus tau xy into cos 2 theta. This is the equations to calculate the shear stress. What we do here, the shear stress is maximum. That means we can differentiate the sigma t with respect to what is the variable here, the angle. So with respect to theta, we can differentiate and then equate it to 0. Okay, so differentiate this equation and equate it to 0. So this is the procedure showing differentiation and equated to, see this, we differentiate that and finally we got sigma x minus sigma y cos 2 theta equal to minus 2 tau xy sin 2 theta. From this sin 2 theta by cos 2 theta is equal to tan 2 theta s. Here from this we give theta s because after differentiation and equated to 0 we should change the theta into theta s. We got tan 2 theta is equal to this one. So from this theta s is equal to 2 theta s is equal to tan inverse of this minus sigma x minus sigma y by 2 tau x1. And after divide with the 2 by 1 by 2, we got theta s. We got the position of this plane of maximum shear stress. Then what we do? Just substitute this theta s value in this equation. Replace this theta with this theta s. But when we replace this theta with this theta s, this equation may be a complicated one. So instead of replacing this theta value, we replace this sin 2 theta and cos 2 theta. For that, again we use the triangle method, rectangle triangle method. Here this angle is equal to 2 theta s. Again, this angle is 2 theta s, and the opposite, the numerator minus of sigma x minus sigma y, that is the opposite side, and adjacent side is the denominator. And using this Pythagoras theorem, we can calculate the hypotenuse, root of this value, so square of this value plus square of this value, take the root of the sum, the hypotenuse. From this cos 2 theta is, what is the cos 2 theta is? Adjacent side by hypotenuse, sin 2 theta is equal to opposite side by hypotenuse. We got this 2 value, supply this 2 value in this equation, replace this sin 2 theta and cos 2 theta. Instead of replacing the theta, we replace the entire sin 2 theta and cos 2 theta. After replacing and the simplification, we got this value, sigma t. That is a maximum and a minimum shear stress. Because after this we have plus or minus sign. We have plus or minus sign here. So here this is the maximum shear stress value. The shear stress acting on this plane, the maximum shear stress. Similarly, there will be another plane with the minimum shear stress. That is at an angle 90 degree with the plane of maximum shear stress. So this is the plane which is containing minimum shear stress, that is sigma t minimum. Maximum shear stress is plus 1 by 2 root sigma x minus sigma y whole square plus 4 tau x by square, and minimum is minus of half into both are actually minimum means the direction is just changing. Okay, so plus something, for example, maybe maximum shear stress is plus 100 and the minimum shear stress is minus 100. Just to change the direction of the stress, that is maximum and minimum. So we got the plane containing maximum shear stress and the maximum shear stress value using this equation. This equation is to calculate the maximum shear stress, and this equation is used to calculate the plane of maximum shear stress. And from these two equations, the plane of this equation is to calculate the plane of maximum shear stress and the plane of maximum principal stress. When we multiply these two equations, because here we can see this is 2 tau x by sigma x minus sigma y, and in this sigma x minus sigma y by 2 tau xy into minus of. So the just interchange the denominator and numerator of this and the extra minus sign. So when we multiply these two equations, we got minus 1. We got minus 1. What is the inference from this equation? Tan 2 theta p into tan 2 theta s is equal to minus 1. That means the 2 theta s and 2 theta will be 90 degree apart. For example, tan A into tan B equal to, if it is minus 1, the A and B will be 90 degree apart. Okay, that is the geometry. So here 2 theta P and 2 theta S are 90 degree apart. So theta S and theta P will be 90 by 2, 45 degree apart. So that means the plane of, that means the plane of principal stress, that is theta P angle, plane of principal stress and plane of maximum shear stress will be 45 degree apart. Okay, the plane of shear stress, maximum shear stress, this is the plane which contains maximum shear stress, and this is the plane which contains maximum normal stress or principal stress, and those two planes will be 45 degree apart. That is the conclusion from this formula. Okay, and this is the final. One more thing, what will be the normal stress on this plane of maximum shear stress? What is the normal stress on the plane of maximum shear stress? Is it 0? In the plane of maximum normal stress, we got shear stress is 0 on a principal plane. Plane of maximum normal stress, we got shear stress equal to 0. But is it 0? The plane of maximum shear stress, the normal stress is 0 or not? How can we check? Just to substitute this theta s value where? In the sigma n equation. In this sigma n equation. And after substitution, and same way, instead of substituting directly this theta s, substitute sine 2, calculate the sine 2 theta and cos 2 theta using the rectangle triangle method, and then substitute here. After substitution, we got it is not 0, that is equal to sigma x plus sigma y by 2. Okay, sigma x plus sigma y by 2. That means the average stress, sigma x plus sigma y by 2, what is that? Here, this is the sigma x, this is the sigma y. So sigma x plus sigma y by 2 will be the normal stress acting on a plane of maximum shear stress. Plane of maximum shear stress. So, actually these topics are not in your syllabus. The transformation of stress and strain is not in your syllabus, but the graphical method to calculate all these values, that is more circle method, that is in your syllabus. So, but understanding of this formula and the concept of principal stress and principal plane, maximum shear stress plane, all these things are important to draw a Mohr circle, or to understand the procedure of Mohr circle methods to calculate the principal plane, principal stress and maximum shear stress, etc. So that is why I take this portion, and this is the conclusion. We have a body, sigma x is acting, sigma y is acting, shear stress tau xy is acting, tau xy is acting. On this plane, on this body, this is a condition, plane stress condition, because here we have only two stress components in the normal direction, and sigma x is equal to 0, and tau xz and tau yz is equal to 0. That is why it is plane stress condition. And in this this is a plane that is at an angle theta with the vertical. Theta with the vertical. What is the normal stress? Sigma n. Sigma n is the normal stress. Okay, sigma n is the normal stress. And we already find out the formula, discuss the formula, that is, this one is the formula. Okay, this one is the formula. The next one, the shear stress on this plane, that is sigma t. Sigma t is the shear stress on this plane. For that, we have the next formula. These two formula, the input values recorded in these two formulas are sigma x, sigma y, tau xy, and this theta value. These are the input values. Okay, and there are infinite number of planes with a different theta value, and out of this infinite number of planes, we have one plane that is called principal plane. That is called principal plane, where normal stress will be maximum. Normal stress will be maximum, and the shear stress will be sigma t. I am giving sigma t, or we can give tau. Tau value equal to sigma t, or tau value equal to 0. What is the angle? The angle between the vertical and this plane is theta p. And to calculate the theta p, or to calculate the position of the principal plane, this is the formula. This is the formula. The 11th formula. Okay, this is the formula to calculate the position of theta p. And after that, we substitute that formula on the general equations, and then we calculate the sigma n maximum, or sigma 1. Sigma 1. That is this formula. So this is the major principal plane. Similarly, we have another principal plane that is called minor principal plane. This is the minor principal plane, where sigma n is minimum. Normal stress acting is minimum. Sigma n minimum, or sigma 2. Sigma 2. Where also sigma t is 0. Sigma t equal to 0. And formula to find the sigma 2 is this one. Okay, the 13th formula. Minor principal stress. And next one is, we have another plane. Just a second. We have another plane. This one. This one is the another plane. That plane is at an angle theta s. That plane is at an angle theta s with the vertical, where shear stress will be maximum. Shear stress will be maximum. How can we find the position of that plane? How can we find the position of that plane? Using this formula. We can find the position of that plane. And we, from this tan 2 theta p and tan 2 theta's formula, we got the angle between these two planes, that is major principal plane and the maximum shear stress plane, will be 45. this angle will be 45. And theta s value equal to this one. This is the theta s, maximum shear stress. And so this is maximum shear stress, sigma t maximum. And on this plane, there is a normal stress on this plane, and that is equal to sigma x plus sigma y by 2. Okay. So this is the transformation of stress on strain, and this is the final figure. This is the principal plane, sigma 1. Shear stress is 0 in this principal plane. Another principal plane that is at an angle 90 degree with the major principal plane. This is minor principal plane, where sigma 2 is the minor principal stress, where also shear stress is equal to 0. From the major principal plane at an angle 45 degree, this is the plane called maximum shear stress plane. On this maximum shear stress plane, maximum shear stress is acting. That is at an angle 45 with the principal plane. And the normal stress acting on this maximum shear stress plane is sigma x plus sigma y by 2. And one more plane, this one. One more plane, this one. That is the plane of minimum shear stress. That is minus of maximum shear stress. And plane of maximum shear stress and the plane of minimum shear stress also 90 degree apart. This is the transformation of stress and strain. So these are the important points. The principal stress represents the maximum and minimum normal stress at a point on a plane called the principal plane. When the state of stress is represented by principal stress, no shear stress will act on that element. The state of stress at a point can also be represented in terms of maximum plane shear stress. In the case, the normal stress will be average stress. This sigma x plus sigma y by 2 is the normal stress on a principal plane of maximum shear stress. That will be average stress. The element representing the maximum plane shear stress will be an associated average normal stress is oriented 45 degree from the element representing the principal stress. So that is about transformation of stress and strain. So here we have total 8 formulas. To calculate the normal stress on an arbitrary plane and the shear stress on an arbitrary plane and principal plane and major principal stress, minor principal stress, and the angle of principal plane, maximum shear stress, angle of maximum shear stress, and the normal stress acting on a maximum shear stress plane. So there are 8 formulas to calculate all this stress components on a different planes. So using this 8 formula, we can calculate all the things. Okay, 8 formulas. And another method is graphical method. And for all the 8 formula, what are the inputs? Inputs are sigma x, sigma y, tau xy, sigma x, sigma y, tau xy, and the angle theta. For 8 formula, these are the 3 inputs. Using these 3 inputs, we can calculate the principal stress, principal plane, maximum shear stress plane, and the stress on an arbitrary plane. Everything we can calculate. Okay. So this, instead of using this 8 formula, using these inputs, we can calculate this principal plane, principal stress, maximum shear stress plane, all those things using graphical method. And that graphical method is called Mohr circle method. Mohr circle method. So we will discuss this Mohr circle method in the next lecture. So that is the graphical method to calculate all the stress components. Instead of using these 8 formulas which we discussed in this lecture, we can use the graphical method. We will discuss this graphical method in the next lecture. Thank you.